Hey, welcome to today's flip lesson, which is day one of a couple days that we're going to spend learning how to solve equations involving square roots, involving radical symbols. So this is a day where you're expected to take your own notes, so make sure you have out notebook paper. Take notes, and when I ask you to pause the video and try a problem, actually pause the video and try the problem. It's great practice. It's a good way for you to get reinforcement if you're doing something well, or to find out if you made a mistake. You can hone in and find where that mistake is. So today, let's start out with just a problem. Let's say we're given this equation right here, and you have to solve it. So you'll notice that a square root appeared in the equation, and nothing's new. Our goal is still the same. We want to get x all by itself. And if you look, the easiest way to get x by itself is to undo the multiplication that's happening. So I'm going to divide both sides by the square root of 5. And when I do that, of course, that makes a 1. And I'm left with x equals 10 divided by the square root of 5. However, that's not entirely the correct answer here. The correct answer is this, 2 radical 5. And I know you're sitting there and you're thinking this. How on earth did you get that? Why is it not 10 over radical 5? And this is the reason why. There's an old rule back from the days before calculators that states you cannot have a square root or a radical symbol in the denominator of a fraction. Although later on, you'll not worry about this rule, it does show up, and it will show up on the ACT and the SAT. So if you're solving a problem like this on the ACT or SAT and it's multiple choice, instead of seeing this as one of your options, it might be this. And we need to figure out, how do you get that? So let's take a look at how you deal with this square root or radical in the denominator. So the process of getting rid of a square root in the denominator is called rationalizing a denominator. And what that means is we want to make the bottom, the denominator, a rational number. And I'll remind you that a rational number is any number that can be written as a ratio, notice the root word, a ratio of integers. So, anytime you have a ratio of integers, like 3 over 4, that's a rational number. Even the number 8, because if you wanted to, you could write 8 as 8 over 1. It is a ratio of integers. You could have 9 over 5. It could be an improper fraction. You could even have negatives, negative 13 over 2. So the denominator can't be irrational, can't have a square root. It has to be rational. And you may remember from algebra and geometry that square roots are not rational numbers. They're irrational. So what we need to do is we've got to get a jailbreak. So how are we going to make a jailbreak happen? Well, there's only one number that can free this 5 from its square root prison, and that is a twin. So I'm going to multiply both the bottom and the top by the square root of 5. Now, I chose the square root of 5 so we can have a jailbreak in the bottom. And, of course, I did it in the bottom and top because I'm really just multiplying by a big 1. And you can always multiply by 1 and it doesn't change the value. So in the top, multiplying straight across, we have 10 times radical 5. Remember, numbers outside of jail don't mess around with numbers inside of jail. And in the bottom, the square root of 5 times the square root of 5, well, that's a jailbreak. One 5 gets out, the other one's not so lucky. And then we end up with 10 radical 5 over 5. Now, look at the numbers that are not in jail. These two numbers here. We can simplify 10 over 5. 5 goes into 5 once, and 5 goes into 10 twice. And so ultimately that gives us 2 radical 5 over 1. That's our answer. That's how we rationalized the denominator. So I think we need a little bit of practice just rationalizing denominators. So let's go for that here. Let's see if we can get some practice. So this would be a good time to maybe pause, because I might be talking faster than you can write. And let's see if we can rationalize the denominators. We can clean up these fractions and make them appropriate for what we need them to be. So this first batch right here, you see in the bottom we have a radical 2. And the rule is you can have no square roots or cube roots, no radicals in the denominator. So the only thing to free a 2 from square root prison is another 2 in square root prison. So I multiply by a big 1, radical 2 over radical 2, and then just multiply straight across the top. In the top we get 3 radical 2, and in the bottom we just have plain old 2. And then I look outside my radicals, and I ask myself, can I simplify 3 over 2? And no, I can't, so that's it. That's my answer. Over here, I see I have a radical in the bottom. I can't have that. So I need to free this 3 from square root prison. There's only one number that can free a 3, and that's another 3. Looks just like it. Multiply straight across the top, multiply straight across the bottom. And that's where 7 radical 3 in the top comes from. And of course in the bottom we get a jailbreak. 1 3 gets out, the other one didn't make it. And then you just look at these two numbers, 7 and 3, and you say, well, they're both outside of prison. Can we simplify? And the answer in this case is no. Let's try a couple more that are a little bit more work is involved. Let's look at this one. Again, it's not simplified because you have a radical in the denominator. So think about what you have to multiply by so this 2 can break out a square root prison. And again, it's radical 2 over radical 2, a giant 1. And in the top, we multiply straight across and get 8 radical 2. And in the bottom, we get just a 2. Again, twins, 1 gets out, 1, well, not so lucky. And in this case, we look at these two numbers right here that are outside of square root prison, and we ask ourselves, well, can we simplify 8 over 2? And absolutely we can. There's a number that goes into both 8 and 2, and that number is 2. 2 goes into 2 once, and 2 goes into 8 4 times. And so after we simplify, in the top we have 4 radical 2, and in the bottom we have a 1, which just 4 radical 2 is fine. This last one, number 4, again, we can't have a radical in the denominator, so I multiply by my big 1, go straight across the top, straight across the bottom, and we look outside the square root, and outside the square root, yes, there is a factor that goes into both 10 and 6, and that factor is 2. 2 goes into 6 3 times, 2 goes into 10 5 times, and so we end up getting in the top 5 radical 6, and in the bottom a 3. So, having done all that work, you might start to wonder, could there be another shortcut club? And it turns out that there kind of is. There are kids who can do this rationalizing in their head. And let's see if you're one of them. And if you're not, that's okay. I mean, none of these problems took us that much time. So let's take a look and see if you can rationalize the denominator of these two pretty quickly in your head. This would be a good time to pause, see if you got the right answer. And, if you need to go ahead and use our big 1 like we did up here, do that. Welcome back. Hopefully you got 7 radical 5 over 5 here. Hopefully you got 8 radical 6 over 6 here, but you realize that, yes, you could take this further and took it down to 4 radical 6 over 3. Again, remember, we can only simplify numbers outside of square root prison with other numbers outside. This 6 and this 6, nope, they're two different things. This 6 is in prison, This one's not. So let's go back to the main focus of today's lesson. And the main focus is being able to solve equations that have radicals in them. So here are two problems that I'm just going to walk you through, and then I've got just a short amount of problems for you to do on your own. Today's homework is, once you've seen this video, to try the handful of problems that I gave you. So here on this problem, problem number 1, we're just trying to get the x by itself. So I'm going to divide both sides by radical 3. And those go away. And you're left with x equals 6 over radical 3. And when you play around with it, you ought to be able to come up with this. And again, there are some intermediate steps you probably took, such as x equals 6 over radical 3. You probably multiplied by radical 3 over radical 3. And that gave you x equals a 6 radical 3 in the top and just a plain old 3 in the bottom. And when you simplify that by looking outside, numbers outside of prison can associate with other numbers outside of prison. 6 divided by 3 is 2. So that's where the 2 radical 3 came from. Over here on this side, again, our goal is to get x by itself. Now I notice there's a 6 and a radical 2 both attached to that x. So if I divide by both the 6 and the radical 2 on both sides, the 6's go away, the radical 2's go away, and I end up with x on the left side, and on the right side, that big old nasty beast. Now, let's take a look at what we've got going on here. There are a couple things going on here. We have a radical in the denominator, but we also have 24 and 6, both outside of prison. What number goes into both 24 and 6? 6 does. 6 goes into 24 once, or 6 goes into 6 once. 6 goes into 24 4 times. And that gives me this. 4 over radical 2. Again, you cannot have a radical in the denominator. That's just this old rule. So I have to multiply by radical 2 over radical 2. And when I do that, I get a 4 radical 2 in the top. And in the bottom, radical 2 times radical 2. We have twins. One gets out, one not so fortunate. And we have 4 radical 2 over 2. The last thing we do, look outside of prison. 4 and 2. Those simplify, and that's how we get our final answer, which is 2 radical 2. So, like I referred to earlier, you have a homework assignment. It's got some problems where you just have to practice rationalizing the denominator, and some problems where you're actually solving for x. Make sure that is done before class starts tomorrow. Good luck.